Welcome to another episode of the Overkill series, where we solve a pretty easy math problem using absurdly complicated means in order to highlight some maybe facts in mathematics that you haven't seen before. So here we're going to prove an inequality, and it's a compound inequality, that 12 over 7 is less than or equal to 2, which is less than or equal to 7 over 3, which is less than or equal to the square root of 7. And we're going to use something called the harmonic-geometric-arithmetic-and-quadratic mean inequality. And that says for all positive real numbers, x1 up to xn, this inequality holds. So notice on this left-hand side, we have n divided by 1 over x1 plus up to 1 over xn. That's called the harmonic mean. Here we have what's called the geometric mean, which is the product of x1 up to xn and then the nth root. This is the kind of normal arithmetic mean, which is the sum x1 to xn divided by n. And finally, we have the quadratic mean, which is the sum of the squares x1 squared up to xn squared all over n, and then you take the square root of that whole thing. So we're going to prove these one at a time, starting with the arithmetic quadratic mean inequality, but we need a tool to use before we get to that. And that tool is called the Cauchy-Schwarz inequality. And it says if we've got two n-dimensional vectors with entries in R, in other words, u and v are in Rn, then if you take their dot product and absolute value, that will be necessarily less than or equal to if you take their magnitudes separately and take that product. So in other words, the absolute value of u dot v is less than or equal to the magnitude of u times the magnitude of v. So in fact, we can choose vectors u and v carefully so that this Cauchy-Schwarz inequality automatically becomes this arithmetic quadratic mean inequality. So let's go ahead and do that. So I'm going to set u equal to the vector x1 over n, x2 over n, all the way up to xn over n. So notice that's just a scalar multiple of the vector x1 up to xn that has been scaled by 1 over n. And then the next thing that I'll do is I'll set v equal to the vector with all entries 1. Okay, great. And now what I want to do is notice if I take u dot v and take the absolute value of that, well, that's going to be exactly the absolute value of x1 plus up to xn over n, but I can actually get rid of the absolute value because I've made this assumption that x1 up to xn are all positive. Great. But then by Cauchy-Schwarz, so let's go ahead and point out that here we're using the Cauchy-Schwarz inequality. We know that that is less than or equal to the magnitude of u times the magnitude of v. So let's see what those are in this case. So in this case, the magnitude of u will be the square root of x1 squared over n squared all the way up to xn squared over n squared. Great. And then the magnitude of v is going to be the square root of 1 squared plus up to 1 squared. And I should point out that there are n ones in this case. So notice we can like simplify this a little bit. That's going to give us the square root of x1 squared plus up to xn squared all over n squared times the square root of n. Great. But now what we can do is slam these square roots together, and that will have the effect of canceling this thing out in the numerator and canceling the squared from the n in the denominator, which, after carefully looking at the extreme left and right hand side of this inequality we have built, we see that we have arrived at our arithmetic quadratic mean inequality. And now we're ready to move on to proving the geometric arithmetic mean inequality. But we need some multivariable calculus for that. In fact, we need the notion of Lagrange multipliers. So let's recall what we get from there. So Lagrange multipliers allow us to find the maximum or minimum, in other words, the extreme values of a function with more than one variables subject to one constraint or actually multiple constraints if we need. So the basic setup goes like this. So we'll assume that f and g are nicely defined functions, like they're smoothly differentiable and stuff like that. The extreme values of f of x1 up to xn, so that's a function of n variables, subject to the constraint g of x1 up to g of xn equals this constant c, occur when the gradient of f equals lambda times the gradient of g. So I've got a whole multivariable calculus playlist where we do this kind of stuff if you're interested. Okay, so now what we want to do is carefully choose the function f of x and g of x so that we can build this geometric arithmetic mean inequality. And the way we will do it is as follows. So let's go ahead and set f of x 1 up to xn equal to the nth root of x1 up to xn. Great. And then the next thing that we'll do is set g of x1 up to xn equal to the sum x1 plus up to xn, and we'll say that's just equal to some constant. So in other words, the sum of all of these inputs is a constant. And so now we know by the theory of Lagrange multipliers that this extreme occurs when the gradient of f equals lambda times the gradient of g. So in other words, taking the gradient of f gives us the partial derivative of f with respect to x1 in the first entry, the partial of f with respect to x2 in the second entry, and so on and so forth. So I just want to notice really quick that if we take the partial of f with respect to xi, well, that's the same thing as the partial with respect to xi of x1 up to xn to the 1 over n. Now notice x1 up to xn are all constants except for xi. So it's not a huge reach to show that this is equal to the following. So it'll be equal to 1 over n, and then the nth root of x1 up to xn divided by xi. So you think about this, you've got xi to the 1 over n, so that 1 over n comes out front, you subtract 1 from that, but that's the same thing as dividing by this xi term. Okay, great. But now the next thing that I want to notice is that that is exactly equal to the original function, f x1 up to xn over n times xi. Great. Then the other thing that I want to notice is that the partial of g with respect to xi equals 1, because that's just a sum of all of the entries there. Okay, great. So now what I want to do is use these two partial derivatives to build a vector equation like this, gradient f equals lambda gradient g. So let's do that. Okay, so that gives us the following equation. So I've taken the gradient of f, but notice I've factored out this constant term. I shouldn't say constant term, I mean scalar multiple. So we've got f of x1 to xn over n times this vector, which is 1 over x1 up to 1 over xn. So all of this left-hand side is the gradient of f, as we sketched out on the last board. And then times lambda, the gradient of g. So notice that's just going to give us lambda, comma, and so on and so forth. That's because the gradient of g was just 1, 1, 1, and so on and so forth. And I should say our constraint equation is still this x1 to xn equals c. Okay, great. But now notice that that tells us that each of these components must be equal to each other, because the right-hand side, all of the entries are exactly the same. And the left-hand side, all of the entries are just very simple functions of x. So in other words, this entry is 1 over x1. We can think about this as a common multiple of all of them, so we can almost disregard it. The second entry will be 1 over x2, and so on and so forth. So let's notice that this tells us that x1 equals lambda times n over f of x1 up to xn. But there was nothing special about x1 here, so we really could have put xi here, and this is going to be for all I from 1 to n. So the important takeaway here is that all of these xi values are the same. But into the constraint equation, that tells us that all of these are the same. So these are all equal to xi, which means on the left-hand side over there, we have n times xi equals c, which tells us that xi equals c over n, and that's going to be true for all I, which are between 1 and n. So that is where our extreme occurs. So let's go ahead and point that out. So extreme is at x1 comma up to xn equals c over n all the way up to c over n. Great. So in other words, when all of the entries are exactly the same. So now we can go ahead and plug that into the original function to see what the extreme is. So into f, that gives us f of c over n, comma, all the way up to c over n, will be the nth root of the product of all of these, which is equal to c over n. But notice c over n is exactly equal to x1 plus xn over n. So in other words, the extreme value of f of x1 up to xn will be x1 plus x2 plus all the way up to xn over n. That's the maximum that this can be, subject to this constraint. Now, how do we know that it's a minimum? So what we want is for this to be a minimum. And we can find out that it's a minimum by testing another test point. So let's notice if we take x1 equal to c, and then x2 equal to all the rest of them equal to xn equal to c, we will get f evaluated at this. So it's c comma 0 comma 0 and so on and so forth. So that still works with our constraint. That will be equal to 0 because we have the nth root of c times a bunch of zeros. But that is going to be less than or equal to f of c over n comma up to c over n, which tells us that this is in fact a maximum. But notice that means that the arithmetic mean is a maximum value of the geometric mean, which makes the arithmetic mean bigger than or equal to the geometric mean, thus establishing this inequality. And now we're ready for the final inequality, which is the harmonic geometric mean inequality. And we're going to prove this with induction, which means we need to establish a base case. That base case will be n equals 1, but I'll notice that n equals 1 is trivially true, so we're not actually going to check that. The n equals 1 case is really just 1 over x1, so that's just x1, but that's equal to x1, which is less than or equal to, well, exactly this geometric mean right here. Okay, and then the next thing that we need to do is make an induction hypothesis. So in other words, what we want to do is suppose that this statement is true for n equals k, which is bigger than or equal to 1. So in other words, if we've got k numbers and put them together in this harmonic mean situation and this geometric mean situation, we get the following inequality. Okay, great. And then next, let's go ahead and suppose that we are given k plus 1 numbers. So suppose that we've got x1, x2, up to xk plus 1, and those are all bigger than 0. So they're all real numbers. And the next thing that I want to do is tweak these a little bit so I can use my induction hypothesis. And I'm going to tweak these by setting y equal to x1. So just the number y is the first one. And then after that, we're going to set y1 equal to x2 over y, y2 equal to x3 over y, all the way up to yk is equal to xk plus 1 over y. Then next, what we'll do is apply our induction hypothesis to this thing that I've boxed in orange. In other words, we have supposed this thing is true for k numbers. We're going to apply that to the k numbers which are given by y1 up to yk. So in other words, our induction hypothesis implies the following inequality. We have k over 1 over y1 plus up to 1 over yk is less than or equal to the kth root of this product y1 up to yk. Okay, great. And then from here, what I want to do is get rid of this kth root and turn it into a k plus first root. So we'll take this equation and raise it to the kth power over the k plus first power. Okay, so let's see what that gives us. So that means we have the following inequality. So notice raising to that power will maintain the inequality. So we have k over 1 over y1 plus up to 1 over yk, all to the k over k plus 1. And that's going to be less than or equal to the k plus first root of this product y1 up to yk. Notice this kth power got rid of the kth root, and now we have a k plus first root. And now what we'll do is make the following claim, which will finish it off. And that claim goes like this. So let's go ahead and set x equal to 1 over y1 plus up to 1 over yk, just for simplicity. So k over x to the power of k over k plus 1. So using our new notation, that's the left-hand side of this inequality, and we want to show that this left-hand side of the inequality is always bigger than or equal to k plus 1 over 1 plus x. Great. And so let's go ahead and sketch out what that would give us to the left of this inequality to see how that helps. So I'll just put like a yellow dot right here to say that if we show that that is true, then we can extend this inequality to the left, and we have k plus 1 over 1 plus x, but notice x is 1 over y1 plus up to 1 over yk plus 1. Great. And then from there, we're home free because we can take both sides of this inequality, which I'll underline in blue, and multiply them by x1, which is equal to y. So if we multiply this by x1, but in the form 1 over x1, and if we multiply this by x1, we'll end up with the k plus first case, thus completing our induction argument. So now that we have this sketched out, all I'm going to do is go ahead and prove this inequality on the next board, and that'll finish off this harmonic geometric mean inequality. So we've been proving this harmonic geometric mean inequality using induction, and on the last board we argued that the very final step of our induction would be proven if we can prove this inequality. So we've got k over x to the power k over k plus 1 is bigger than or equal to k plus 1 over 1 plus x. Okay, so let's see how this goes. So I'm going to start off by taking the natural log of both sides. That's going to simplify this because this will turn this exponent into a multiplier. So taking the log and using some natural log rules, that will give us k over k plus 1 times the natural log of k over x is bigger than or equal to the natural log of k plus 1 over 1 plus x. And I should point out that what I'll do is manipulate this inequality until we get something that's obviously true. So maybe I should call this like a proof in quotes because we're being a little bit sloppy. It's not so much constructive, but we're showing that we have an equivalent statement to this, which is exactly true. Okay, so the next thing that we'll do is use logarithm rules involving a quotient in the argument of the log. And also I'm gonna go ahead and multiply this k plus 1 over to the other side of the equation while I'm at it. So let's see what that gives us. That gives me k times natural log of k minus natural log of x is bigger than or equal to k plus 1 times the natural log of k plus 1 minus the natural log of x plus 1. Great. And so in other words, the inequality right here is equivalent to this inequality. And then again, since the natural log is an increasing function, that is equivalent to our goal inequality. Okay, so now what I'll do is I'll go ahead and subtract this term from both sides and set that equal to f of x. So now let's go ahead and set f of x equal to, like I said, the difference as we move this over. So that's going to be k times the natural log of k minus k times the natural log of x minus k plus 1 times the natural log of k plus 1 plus k plus 1 times the natural log of x plus 1. Great. And now notice that this inequality holding is the same thing as showing that this f of x is always bigger than or equal to 0, just because of the arithmetic of us moving these things over. And the next thing that we'll do, which is straightforward but a little bit too much work for this, is to argue that we have a global minimum of this function f of x at x equal k. So a global minimum. And then another thing which is pretty easy to check is that if we plug k into this function f, we'll get 0. So notice that's because we have k natural log of k minus k natural log of k. Those are going to annihilate each other. And then furthermore, these terms are going to annihilate each other. So if we have a global minimum at x equals k, well, and that global minimum is 0, then that means that this function is always bigger than or equal to 0. But recall, this function being bigger than or equal to 0 is equivalent to this inequality, which is equivalent to this inequality, which is equivalent to our claimed inequality. But our claimed inequality finished the induction step of this harmonic geometric mean inequality. Now we'll apply this inequality to a set of numbers in order to retrieve our goal inequality. So let's say that we have n equals 3, so we need 3 numbers. I'll go ahead and set x1 equal to 1, x2 equal to 2, and x3 equal to 4. So let's see what we have here. So we'll have 3 over 1 over 1, so that's just 1, plus 1 over 2 plus 1 over 4. So that's the harmonic mean of those 3 numbers. But that needs to be less than or equal to the geometric mean, which is the cube root of 1 times 2 times 4, which is going to be less than or equal to the regular mean or the arithmetic mean of those numbers. So that's 1 plus 2 plus 4 over 3, which is going to be less than or equal to the quadratic mean of all of those numbers, which is the square root of 1 squared plus 2 squared plus 4 squared all over 3. Now let's go ahead and do simple arithmetic to calculate these. So notice if we add these two numbers together, 1/2 and 1/4, we get 3/4. And then if we go ahead and add 1 with 3/4, we're going to get 7/4. Great. But now if we do 3 divided by 7/4, that's going to give us 12 over 7. Great. But now if we do this multiplication, notice that those multiply to 8, but then the cube root of 8 is 2, so that means 12 over 7 is less than or equal to 2. Then 1 plus 2 is 3, plus 4 is 7, so we have that is going to be less than or equal to 7 over 3, which is less than or equal to, well, notice this numerator here is going to be 16 plus 4, which is 20 plus 1, which is 21. So we have 21 over 3, but we need to take the square root of that, and so that is the square root of 7. So we've proven our goal, and that's a good place to stop.